So I watched that video and realized I could say this a lot quicker. So when something is on an inclined plane, we have a bit of an issue because the direction of acceleration is along the direction of the ramp. So that's our important direction to do net force equals ma for. But our force of gravity isn't aligned with that. So we need to break our weight vector, or our force of gravity vector, into components that are parallel and perpendicular to the incline. So what this looks like is we use our normal force as a nice normal or perpendicular direction, and we draw in the sides of a right triangle that would create this vector as the hypotenuse of that right triangle. So we have this one, which I call FG perpendicular, because it is perpendicular to the ramp. And then we have this one, maybe that pink shows up, which is parallel to the ramp, FG parallel. And the right angle is right here between the perpendicular and parallel directions. So the key to this is this angle here shows up right here in this triangle. So a short proof would say that I can extend this line and this would be a 90-degree angle. And so this angle up here would be 90 minus theta. And so that angle has to be theta. There's a short one. I can do that in person if you want that more. So we need to express the force of gravity perpendicular and the force of gravity parallel in terms of the hypotenuse, the force of gravity, and the angle theta. We're going to use trig to do that. So FG is what I would call the adjacent side if I'm doing SOHCAHTOA. So FG perpendicular is equal to FG, which is the same as mg. So I'm just going to put that in, times cosine of theta. And then FG parallel equals mg sine theta. So we have this mass, capital M, that's at rest on a rough surface with friction with an incline of 0 degrees above the horizontal. In terms of mg and theta, derive or determine the magnitude of the frictional force and normal force that are keeping the mass in equilibrium. So it's in equilibrium. So this is critical. So then instead of doing our sum of the forces in the x and sum of the forces in the y, what we're going to do is the sum of the forces perpendicular to the ramp is equal to 0 because it's not accelerating up off the ramp or down into the ramp. So that means the normal force plus FG negative FG perpendicular rather equals 0. And so that means Fn equals FG perpendicular. Or Fn, to put it in terms of m and g and theta and math, is capital Mg cosine of theta. And then the same goes for the parallel direction. So we're going to say the sum of the forces in the parallel direction is 0. It's at rest. So that means this is the static force of friction, or FFS, or FF static. So that means, by the same way that the force of friction, which we'll call negative, plus FG parallel equals 0. So FF equals FG parallel. So FF equals capital Mg sine of theta. And so that's kind of interesting So if we say, assuming theta is the largest angle with which the mass will not slide, use your answers above to come up with an expression that could represent the static coefficient of friction. So we know that mu S or K is equal to the force of friction, in this case static, divided by the normal force. So we're just going to plug in this here and this here and see what happens. So I'm going to switch back to the red. So we get mg sine theta over mg cosine theta. And so what we end up with is the masses cancel, the g's cancel, and cancel just means 1. And we're left with sine theta over cosine theta. Now you could leave it like that, but there's something cool here. So sine theta, for those who know SOHCAHTOA, is opposite over hypotenuse, and cosine theta is adjacent over hypotenuse. Dividing by something is the same as multiplying by the reciprocal, so that's the same as taking opposite over hypotenuse and multiplying by the reciprocal, so the inverse of that, so hypotenuse over adjacent. And so our hypotenuse divided by hypotenuse becomes 1, and we get opposite over adjacent. Well, that is tangent theta. That's kind of cool. So this is all I wanted you to see.